All right, welcome back to the Bat of Doom track at KernelCon. We got another visionary slide here doing the 3D. I don't know about you guys, but I can't get my glasses to work quite right. Hopefully the ones that you guys got in your swag bags work just a little bit better. It just looks like a normal slide to me. I don't know. Anyway, Heather here, InfoSec Anon on Twitter. Had a really nice CFP proposal as a budding night academic. It's a very well thought out talk, and it's about cybersecurity datasets. And I think it's going to be pretty interesting. So stick around, and then we'll catch you back for questions on the flip side. Take it away, Heather.
All right, as Tim said, I'm Heather Lawrence. I go by InfoSec Anon on Twitter. I'm working for the Nebraska Applied Research Institute. Some information about me: I do some data science. I have done like 3 PhD programs for like the past couple of years. I'm currently with the University of Colorado, Colorado Springs. Before cybersecurity, I was enlisted in the United States Navy, and I've also helped out with Hacking UCF. We won NCCDC one year, a couple of years, and I help out the community in a lot of different ways. I'm kind of going to talk about what our best practices that we discovered were. This is more of like a community thing, and then kind of go into what we did as far as creating a cybersecurity data set, how we designed the whole thing, and some challenges that would probably help you if you decide that you want to either use data or you want to load data to the community, and then some resources and like an outro. So Garib et al., he kind of discussed some best practices in 2016, some ideas like having a complete network configuration, having complete traffic. So not just having the net flows with the payloads removed, but having like a PCAP with the full payload. Having a data set that's labeled. That one's a really important one, and I'll mention that one more later. Complete interaction, so between the attacker and the endpoints, and between any benign nodes and the attacker. So seeing the full conversation, not just one side. Same thing with the complete capture. The protocol variety is super important. So you don't really teach your IDS a whole lot if you're just showing like HTTP and maybe TLS or SSH, like basic protocols. Having a wide protocol variety helps the IDS kind of determine what is abnormal or benign. And attack diversity, right? You want to trade it on multiple different attacks like DDoS or botnets or directory traversal. All of these things that you can't just have one sort of attack and then hope that your IDS knows the rest of them. It's not kind of how that works. And then the feature set is super important. Which features you use, how many you store, what do you train them with? Charlb et al. Has some very similar best practices. Basically, you want it up to date. And this is a big one. You want it publicly available. The data set doesn't really do any good, it turns out, if nobody can actually access it. And again, real network traffic. You wanted the malicious and normal user behavior and the payload. So those are 2 different sources that kind of talk about what the best practices are. So our motivation, like why we did this thing, intrusion detection relies on signatures, right? And signatures can be changed by like changing trivial parts of the attack, generally the payload. So as a security industry, we're like, well, machine learning, that's going to save us, right? Until we discovered that adversarial machine learning was a thing. And several authors since 2010 have complained about a lack of data. And so it's kind of hard to test IDS-specific machine learning algorithms without having usable available data, and you can't compare how you implement those algorithms or what you train them with unless you have data that's open access and available amongst different researchers. So maybe you have no idea what I'm talking about. Adversarial machine learning, it's something that came out in 2004 by a seminal paper from Dalvi et al. It's called Adversarial Classification, and it's basically the seminal paper for adversarial machine learning. Now, the first time that particular phrase comes up, and they talk about adversarial examples later on that can be used to make a machine learning algorithm make the wrong decision. And that's the basis of what adversarial machine learning is. Later on, we discovered that different machine learning algorithms were also affected by this. Basically, if it was differentiable, it had a chance to be affected by different attributes. SVMs, neural networks, logistic regression, all of these are differentiable and can be affected by adversarial examples. More specifically, the types of attacks are causative, so you can manipulate the training data. Data poisoning, so you craft attack points into the training data. You exploit the classifier itself, that's exploratory, or hybrid, so you can have any combination of the above. And the reason why these adversarial examples are useful is something that we theorize is called a blind spot, right? You have a region in the model's decision space where the decision boundary is inaccurate, right? We think that no training data was provided in that area. And so the machine learning algorithm has to kind of guess. And this is an ongoing research area. Computer vision, they've been doing adversarial machine learning for a while. So here on the left, you have practical black box against machine learning. This is Nicholas Paperno. And this is back in March 2017. And on the right, you see we're just starting to talk about attacking machine learning for the network side a year later. So we're easily a year behind computer vision. And of course, there's a lot of funding in computer vision. So theoretically, we're more than a year behind them. All right, so back to the motivation. We can't test, right, without usable data, and that data has to be open access. Well, are there data sets out there that do this? I call it the prototype data set, KDD99. It's the most cited, it's the oldest. 1999, yes, we are still training algorithms training on data from 1999 and assuming that it has any meaning in 2020. It was actually not even real data, it was simulated data, and it's supposed to simulate an Air Force network for a number of weeks. But it doesn't have any of the protocols in the last 20 years, right? And it doesn't contain any real packet headers or data. There's also a later one, NSL KDD, where they tried to improve it, but again, it was a simulated data set as well. There is another one based on SSH attacks from the University of Twente, or Twente. Somebody can correct me on that later. This one is a bigger network, had 100 servers, workstations, and honeypots, but it was limited to only SSH. So remember when we were talking about what we want in a data set, we want a different types of attacks. Well, this one's only an SSH, the data set. But it was nice, then it contained flow data and the host log files. UNSW, this one is out of Australia. Basically, they took the Ixia Perfect Storm tool to generate attacks and then capture them through Broad IDS and generated attack labels. This one's a little bit more diverse. It includes protocols like HTTP and FTP, but it is generated by a tool. So that's not really the best idea for if you wanted to have malicious and benign data to train your IDS with, but it's usable and it's open source, like you could actually get it. AWID, the Aegean Wi-Fi intrusion data set, is another one, but this one is all Wi-Fi. So if you were trying to train on only Wi-Fi data, you could do it on this. The normal traffic is human generated, which is different, right? It's not generated by a tool. This is on an actual network. The attack traffic is generated using Kali Linux. Later on, we have a CTU13. This is 13 PCAPs focused on only botnet traffic. And they introduce a new method for detecting botnet traffic called Bot Hunter. And you can see here that their network is a little vague. It wasn't exactly the detail they put the most effort into. Let's just put it that way. It's also a very large data set, but again, also botnets. The best one that I've seen so far is the CICIDS 2017. Here you can see more of a variety of nodes, right? You see Ubuntu and Mac and Windows. There is actual like switches, and there's a DNS server with things you would normally see in an enterprise network that you don't necessarily see in a lot of the earlier academic data sets. So are there data sets that kind of allow us to train machine learning algorithms and kind of test that decision boundary? Well, not really. There are data sets that have benign malicious, but usually they're not labeled, or they aren't open, or they aren't designed this way, or there's only a certain attack, right? So each data set is really kind of pointed to a specific use. And so this data set that we wanted to do was kind of not listed in this survey. And this is a survey that, it's funny, I was on Twitter, and Jason Trost was like, hey, look at this survey of great network-based intrusion data sets. And I was like, I know that paper because I'm using that paper. A lot of the data that I've mentioned up to now is listed in this paper, and they do compare some of the pros, cons to using each one. For the most part, to save you some effort, some of them are open, some of them only have PCAPs, some of them aren't labeled. It's like you need this huge table to kind of determine what data is best for your research. Our experimental setup to make this data set kind of works like this. We decide that this traffic is benign. Type 1 is a rejection of this hypothesis. So type 1 would be a false positive. And we don't want false positives, right? Increases operator fatigue, and it's classifying benign traffic as malicious traffic, which we just don't want that. And then type 2, which is a non-rejection of the false null hypothesis. So it's a false negative. Basically, we don't want malicious traffic to be classified as benign traffic because that allows malicious traffic on the network, and that completely defeats the whole purpose of this. So, like, what kind of actions on a network could cause these errors? Web surfing, right? If humans on a node on an endpoint and they're just doing their job. True negative, that should not be malicious. True positive, SQLi. There are no circumstances where SQLi is nothing else except a true positive, right? Somebody shouldn't be using SQLi in the course of their job unless maybe they're a pen tester, but it still shouldn't be on the network, right? I'm not trading my IDS on pen tester traffic. I'm trading my IDS on actual malicious traffic. So SQLi here is the true positive. A false positive could be web crawling. Non-malicious actors crawl websites all the time. It's technically allowed. Google does it all the time. You shouldn't do it. However, it's still a false positive. They're not hacking you. They're just scraping content off your webpage. User actions. If the IDS sees something that a user is doing network-wise and it is abnormal, that user doesn't do it very often, it could be a false positive. And then false negatives could be things like in-maps. It could be miscategorized. It should be a true positive, but it's not. Same thing with like directory traversals or deliveries of shells. Our design was a little different. We used 3 server blades running Windows Server 2016. Each drone had only 1 gig of RAM, so it was very bare bones, a single virtual processor. The network tap was the beefiest part of this with 32 gigs of RAM. And we were running everything through an ASA 5506 and a Netgear 24 port switch. From what you can see on the right, it's basically everything went through the switch. You had a lab controller providing internal DNS. The network tap kind of took all the traffic from 20 virtualized workstations between 2 blades, an Exchange server, a wiki server, and a file share. We automated data generation at first. There are 3 profiles that were assigned PowerShell scripts that randomly browse to websites. They email another user using the Exchange server. They read and write to SMP file share, and they browse to wiki addresses. Malicious traffic, we had used Kali Linux like some of the other data sets. And then we also decided that we were going to do human generation as well. So we got IRB approval through the university board, and we interviewed 10 human subjects for 30 minutes, and again for an hour, where they just provided human-generated data, and then they provided malicious traffic for an hour. What we did was we set up DVWA and allowed them to use Burp Suite to leverage vulns in DVWA. And this saved us from having to build our own web app, vulnerable web app, right out of the gate, right? So I'm trying to, as a researcher, train IDSs. It is a significant drawback, right, overhead, to have to consider all of these network pieces and make our own vulnerable web app on top of it. So this is kind of how we lowered the bar of participation, right? Because anybody can leverage a vuln once they know the vuln exists. So if you had like an insider threat, somebody who was very familiar with your internal network, all they'd have to know is that a SQL injection occurs on a certain box or a certain field, and you can look up how to leverage SQL injection. It's not really rocket science, and this was helpful for getting more human subjects. As you might imagine, hackers are not very enthusiastic about providing human-generated data for research purposes. And then our interviews kind of look like what you see to the right. So this is person 7, and they kind of rate their own skills and then walk through what they tried to do in their hour. Data collection kind of worked like this. You had the network tap, which was running Wireshark, and it would save Wireshark as the network traffic as a PCAP and G. We'd take T-Shark and kind of remove some of the retransmissions that we had from the network, which would give us a PCAP, and we run it through something called Joy. Joy is a GitHub project through Cisco, and it provides additional metadata to the PCAP and spits out a JSON object. There are different parts of Joy that you don't normally get through just doing it through a PCAP. Joy will give you fields like entropy, total entropy, standard deviations, right, without you having to do this on your own. And then you take the JSON, kind of put it through Python 3 for pre-processing and get a CSV, and then you train your machine learning algorithms off of the CSV. Data processing, our network traffic captures were QA'd after we gathered them, which is good. Sometimes you mess up the network and you don't realize that STP packets aren't actually going where they're supposed to. And then we verified it's okay, you can laugh at me, it's fine. Attacks were verified via PCAP review. And then we took the ways that we identified the traffic in Wireshark and we translated them into Pandas data frame rules. So with the data set, there's this README that basically says the ground truth. So if you wanted to, completely reanalyze the PCAP, you have the ground truth as to which traffic is malicious and why. So here you see a Python snippet where you're defining a function or a method, and it's basically looking for this particular port number, and it's defining it as a label as 1. And it's basically, if it was from that IP address, then it was a malicious piece of traffic. We had to take IPs and we had to reduce the feature space, essentially. What we noticed before we started virtualizing websites that the users could browse to, we were getting a lot of third-party advertiser traffic. And we're kind of limited on research resources here. So when you have like 300 unique IPs for like a 30-minute session, and most of that is third-party advertisers, you kind of need to reduce the sample space a little bit. And so what we were doing is we were translating an IP based on who that IP or who owns that IP based in the ICANN database. And then we binned ports by a major service. So we're reducing, think about ports, right? 65, 535. You don't want that many features, right? One for each port. That's not how that works. So you kind of bin them by group, like what important ports there are. I mentioned the third-party advertisers. We condensed by ICANN. We use the Maxmind Geolite 2 database, which is open for free. So if you find yourself doing this again, keep that in mind. Also keep in mind that it required multi-threading. The switch statements that we needed to reduce processing, and I think I got it. No, in another slide, I show exactly how much we were reducing the time down to. I'll get to that in a minute. For design priorities, this is for machine learning. So we wanted some of the features to be as best as possible. And we wanted to prioritize plain text machine learning features, which unfortunately requires that HTTP2 and TLS 1.3 need further engineering because they are encrypted. And for HTTP2, it's more compressed. We wanted more metadata from the TLS handshake, particularly from the client hello message, because there is a transaction that occurs that shows which cipher suites are acceptable, and you can fingerprint hosts based on which cipher suites they do and do not accept. But so these priorities were what we wanted: plain text features for machine learning. So we came across some challenges to make it so, right? HTTP2, right? I said it was compressed. And a lot of the Alexa 100 already has HTTP2 enabled. And that it's intended in purpose, right? It's a feature, not a bug. It enhances the user experience because it compresses the traffic headers. They get to reach the website faster and enjoy the content of the website. Unfortunately, you cannot read HTTP2 headers in plain text. So we had to ask the server, please, could you give us not HTTP2, use HTTP 1.1? And you could do that through curl. Here you can see an HTTP2 header, and you can't read anything. Neither will a machine learning feature. So 1.3 to 1.2. 1.3, right, as we all know, removed the cipher suites that plagued 1.2, like CBC. And 1.3 requires ephemeral Diffie-Hellman keys that are established between the user's endpoint and the web server. And so how do we get clear text features if the keys are between the user's endpoint and the web server? Well, what if we ask nicely, hey, website, can you just use 1.2? We were finding that a lot of the Alexa websites would break if you ask them to downgrade, which would require us to have to cherry pick websites that have yet to upgrade to modern crypto suites, which is kind of artificial. It's looked on very poorly on the academic side. And honestly, artificial data isn't very nice because it doesn't train your algorithm very effectively. And then modern libraries, some of them are only providing 1.3 by default. And the share of 1.3 is growing quicker than the adoption of 1.2. So this is like a kind of a concern. TLS 1.3 adoption, if you are not aware, it's about 30% on Chrome as of August of last year. You can see on the right Cloudflare's TLS version trends from 2018 to 2019, and it's still mostly 1.2. And then if you use Qualys's SSL Pulse, you'll see that it is mostly still 1.2 that is supported, but 1.3 is growing. In order to solve the ephemeral Diffie-Hellman keys, we originally came up with the scheme to forward all of the browser Diffie-Hellman keys to the network tap box and to try to use Wireshark to decrypt the packets before saving the packets, or the PCAPs, and using machine learning on them or pre-processing. Can't we just use man in the middle, right? Well, the problem with man in the middle is that we lost data visibility. So you'd have to run one man in the middle proxy, squid proxy per user VM. And if you understand the resources that go into using a proxy server, it was honestly more than we had available to us. And then even if we did use man in the middle proxy, here you see a comment that they don't intend to work on PCAP export in the near future. And that was back in 2016. And then it was referenced again in 2018. So really, this is just not a feature that people are going to give you. And then even with the keys, Wireshark couldn't decrypt the pack or save the decrypted paycaps either. So we asked them nicely, we tried a man in the middle, and then we just tried to like forward the keys, and none of that was working. For future reference, and I didn't know this when I was going through this research, there is a GitHub project called Man in the Middle PCAP, which is an add-on script that does this. And that would have saved us a lot of issues like a year ago, just so you're aware. So Ask It Nicely didn't work. Man in the Middle didn't work. How do we provide these features? We mirrored these websites to control the Cypher suite. And this added artificiality to the data, but it had the upside of removing a lot of the third-party advertiser traffic. The residual traffic we had was TLS 1.3, but it was mostly OS updates. It wasn't through website surfing. And majority of our traffic still uses TLS 1.2. So there was a lot of feature engineering that went into this network data. And then for like the GIP lookups that I was mentioning before, here you see that there's only a couple in the array on the left, and it's taking 1700 seconds to go through and try to do a one class SVM. And then on the right, after we multi-thread, it's down to almost 2.5 with a lot more numbers. My suggestion to you is if you decide to do geo IP lookups in the future, that yes, you're going to need threading, and Jupyter notebooks are slow. So let's say you do a data set. A lot of the network traffic data sets, remember we were trying to go back to our best practices, they said they want the payload, they want the full PCAP. Well, PCAPs are big. They're much larger than net flows. If you have a data set of this size, you might end up paying to host it to provide that data to other researchers. And now I'm going to talk about some of those resources, like some of the hosting that we went through, that will hopefully help you if you decide to produce a data set for the community, or you need to use a data set from the community. I am mostly talking about network-based PCAPs, network-based intrusion. There are also really other cool data sets for malware. If you are not familiar with the Ember data set, is being produced by Endgame. There's also Argus Lab. And many of the data sets that I've mentioned are available over the Canadian Institute for Cybersecurity. They have DDoS, Android malware, the CICDS one that I mentioned before, and a botnet one. Hosting. If you're not familiar with Impact Cyber Trust, it is a more of a formal institution where universities submit their data, but they host their data themselves. And you have to submit as an actual researcher to be able to access any of those data sets. Snap from Stanford is pretty much the same way. The network repository is actually really cool because it goes across multiple domains. It's not just computer science, it's like bioinformatics, network science, physics. And then there's the AWS Dataset program, which they will ask you to be cloud streamlined, right? Because it's AWS. And then if you fail all of those options, well, there's AWS Glacier. And I did the pricing out for it. It's about $210 for about 10 years. The wicket, of course, is that you have to chunk off your PCAPs. I believe the max data size is 4 gigs. So if you have a capture that's 9 gigs, well, you'll have to cut that in at least half. I got a lot of questions like, hey, why didn't you just use the Wall of Sheep dataset? Why didn't you just use the DEF CON dataset? Why didn't you just use the NCC dataset? The problem with these data sets is that none of these are labeled. So NCCDC, right? 2 days, what is it, 6 teams? Then the gold team, white team, and another team, and none of that is labeled over 2 days. Good luck. Some of them don't really even come with like a README as to what endpoints were what. Again, and like with wall of sheep, you'd have to kind of go in and identify which ones are benign and which ones are anomalous. And it's kind of hard to, it's kind of an opinion, right? So it would be hard to evaluate and give the ground truth of any of these data sets because you weren't there. It's kind of easier to build your own and you can tell other people what you did. In the future, I'd like to do things with OT, right? We don't have any OT ones yet. And I'd like to do a capture the flag where we could get more participation. Yeah, nice.
Sorry, there's a bit of chatter going on over here.
I'm almost done, and then we can get some questions. There's major references and questions. I'll take those.
We're trying to suss through. All right, question numero uno.
All right, hit me.
Has there been some consideration on trying to get something like NCCDC to start building their own data sets and then publishing them?
Well, they do publish them through Impact Cyber Trust, right? One of the resources I mentioned, like all the NCC data sets are there for that final competition. But again, you're talking about 30 to 60 gigs of PCAPs that have been chunked up. I think the chunks are either 1 gig or 2 gig each. And you have to kind of thread them back together and kind of figure out what each team was doing and then which one's malicious and which one's not malicious, which can be very hairy.
Yeah. Do you, this is a question from me,
Sure.
not from the thing for whatever that's worth. You kind of went through a lot of different data sets. And I think in academia, especially when you're trying to write a paper or start some new research, there's usually at least some desire to not reinvent the wheel. Like you don't want to like create a yet another data set if there's one that you can run your experiment on or whatever. Do you have any tricks or tricks of the trade, I guess, to like trying to find them? Like the problem is there's not like dataset.org that has like all the data sets, right? So like, how do you go about finding like all of this this knowledge that exists out there?
I have two techniques. One is to go to scholargoogle.com and to kind of use Google Dorks to try to find keywords around data set, right? That specific phrase, and whatever domain you're trying to find data in. That's one. And then the other is to kind of look through papers that have been published in that area and kind of see who they reference. It can be really time consuming to go through like 30 to 50 references and try to figure out which one's a data set. And that's why I try to go the survey route through googlescholar.com, google.scholar.com.
Gotcha. Yeah, that makes sense. Trying to trace down, sort of doing some recursion on references and
exactly
some certain depth.
I would say sometimes Google is better at picking up the keywords at like data set than just trying to brute force it and go through each reference.
Sure. I guess another thing that's always kind of comes up with that is when you finally find a data set and it's labeled something like network intrusion data set 4 or something like that, right? And you want to run some data like a network intrusion experiment on it. How do you sort of ascertain the assumptions that were made on the creation of that data set? You touched on some similar parts earlier where like this is really old and it turns out not a lot of people know this, but it was synthetic and it was created by the Air Force. Like, how do you sort of ensure that you're using a data set in a way that it was intended?
That's kind of on the data set authors. And I hate to say this, but documentation. Other researchers are going to come along your data and be like, I wonder, how was this made? What does this mean? What is this equation? If you don't write any of that down, well, nobody's going to use your data.
Sure. Well, that's I'll push back on that a little bit. People will use it. Just all
That's
the
true.
results will be on flawed assumptions.
No, that's true. That's exactly what happened with KDD 99.
That happens a lot. So there's a question that is a little ambiguous. So I'm going to ask the same question with two different ways because I don't know how they intended it. And rather than ask for clarity, I'll just ask kind of both versions. They want to know how long it took to create the data set. And I don't know if that means like literally the generation of the data set or sort of the project around like planning it all the way to, you know, packaging it.
The project itself was more of a year plus, between going through the IRB process and outlining experimentation and setting up the network and then troubleshooting the network, getting human subjects in, and then trying to sort through all the data, right? It's about a year. If you're talking just about sampling, sampling doesn't, it depends on how long you want to give as a data set. Our particular data set, I believe, there are 4 solid 24-hour baselines. So 4 days of benign traffic. And then there are snippets of faster attack traffic. And the reason why we cut it very fast, very quick, is because it was easier to identify malicious traffic if you only have 15 minutes of traffic instead of having like full 24 hours. And the way machine learning is done, right, on the back end, it doesn't need to be a solid full PCAP that you train on. What they do is they find like records, right, each like packet or net flow, right, each conversation, and it's benign or malicious, and then they stack them together in a CSV, and that's after it comes out of the PCAP and it's processed all together. So it doesn't matter if it's a solid one piece or if it's broken up or not. Depending on how you're training, of course.
Yes. Jesus, sorry, I'm like they're like rolling in now. Here's a sort of a softball for you. I imagine it might be pretty pertinent for a lot of our audience. What is IRB?
IRB, Institutional Review Board. It's super important when it's kind of funny because we have COVID and we're talking about vaccines. The whole idea that you don't test on human subjects without meeting certain ethical standards. This is what IRB does. You submit your entire project like, hey, you're doing human subjects testing. Okay, well, we want to make sure that human subjects are safe, right? And they understand what the research is that they're doing. They understand their rights and that they can back out of it and that there might be some risk. That's what IRB is intended for.
What information is valuable that you're getting out of comparing the data sets? They suggest that they can see TLS data being very useful. What else?
Like what data is useful in the data sets?
I guess the question, maybe we'll get some clarity, but the question is also about comparing the data sets.
So what I've seen with some data sets, and I kind of touched on this earlier, is that some data sets are very like one-trick ponies. There's the SSH one, there's the botnet one, and it only captures really one attack type, but it goes deep into those attack types. So like the botnet one, each capture is a different botnet. It has different mechanisms, different behavior, the way that it's run, and that's kind of important. But you have to kind of read about the data itself to see if it's useful, I guess. I'm not sure if that answered the question.
Yeah, I'm not entirely sure either. Maybe we'll get a little bit of clarity and bounce back to that. We'll see. Kind of an open-ended question. Did you employ any sort of visualization tools in this the design of the experiments or the analysis? And what are your favorite ones for reviewing data sets?
For most of this, I liked using Jupyter notebooks. My kind of workflow, if you will, is to take a subset of some of the larger data and cut it down to like 10,000 rows and at a sampling and kind of pull it into a Jupyter notebook and then kind of analyze it. So I'll do like, you pull it into a data frame and you'll do like data frame.head and kind of look at, all right, well, what are the different features that they're using? Like, how are they continuous? Are they numeric? Like, what are the features? And then I'd use something like scikit-learn Matplotlib and Seaborn to kind of visualize like something in particular. I'd like to see how many protocols they have and how much of the traffic is that protocol. Is it all HTTP? Is it some little bit of TLS? Is it just, I don't know, is it just DNS traffic? I hope not.
Are you just a personal follow-on, I guess, to this other person's question? Are you mostly doing like counts and bar charts and box plots and stuff? Or are you doing things that are looking at sort of more like shapes of data sort of things? It's hard with like port numbers, but other things you can look at like time data.
I'm not quite at I understand what there's huge network maps, so it's kind of like clustering and you're like looking at where things cluster. And that is good to look at. I like to do violin plots to kind of see which features are useful. I like to see what is in each feature, particularly for the attack labels.
Gotcha. Another question. Do you run into system limitations when trying to run data through models? Yes. Especially when trying to bucketize items.
Oh, yes, all the time.
About removing, ad info. I don't know if that's important or not. Maybe that's a typo. You talked a little bit about sampling, but I think the core of the question is, do you run into limitations when you're trying to run data through models?
All the time. I don't think the problem is not enough data in some aspects. Sometimes the problem is too much data. Because the interesting part about network intrusion detection, even with all the data sets out there, is that they tend to be terribly unbalanced. You'll have like 80% of it as benign traffic and web surfing, what have you, and maybe 20%, probably less, is actually attack traffic. So trying to train on that can be very difficult, and you have to kind of curate your data to get the results that you want, unfortunately. As I was mentioning earlier, having that slice of like 10K rows just to kind of set up your pipeline first before trying to add more data is extremely useful in terms of saving time training algorithms.
This isn't particularly related, but I feel like it has a standing chance of being a genuine question. And I think this person would probably stand up and actually ask it. Have you ever had to deal with a parser that just broke? And if it did it ruin your day, or did it break in some sort of comical way?
Honestly, the worst part is when you have a parser that's doing regex and you don't find out that it's failing on regex until you go to look at your data in like a Jupyter notebook, and you're like, that 250 character string is not supposed to be in that field. Where did that come from? And you go back to your regex and you're like, oh, yeah, I totally did not clear enough of what I thought I had done. Similarly, there's when you get into importing like JSON objects, you'll have like a JSON object of nested lists, which can be fun to try to key into objects and pandas. So yeah, I would say a lot of data science is getting the parser to work.
Sure, yeah, there's different stages. There's this whole, before you ever get to do it, you got to make the data ready, right?
Yeah, the algorithms are very specific as to what they will take.
All right, so one more question. I think we have time. I'm going to go ahead and ask it.
Sure.
Since you mentioned ML and AI, the author wants to know, did you discover that there's a future in tracking the cyber kill chain with the blockchain to discover new cyber commodities and SecDevOps capabilities for first strike defense?
I'm not aware of using cryptography to facilitate that need, but it sounds like something I would study.
It sounds like something that you could probably maybe team up with Coldwater on.
That'd be a fun teammate. Totally down for that. We'll send goose memes to each other. It'd be great.
It'll be great. There'll be so much work done.
Yeah.
All right. Well, there were a lot of questions kind of piping in at the end. I imagine that other people might have some if you stick around in Discord.
Yeah, I will be in Discord if you guys want to ask me.
Heather, InfoSec Anon might be a little more challenging to find because her yellow tag trumps her blue tag for her speaker role in Discord. So instead of looking for the blue speaker tag, look for her as a yellow organizer tag. And thanks for the talk and thanks for the work in organizing KernelCon 2020 version A and then KernelCon 2020 version B.
An adventure.
Yeah. All right. So